Hello and welcome back. This is lecture 4 of Systems 556, 750, Simulating Neurobiological Systems. I'm Terry Stewart, and this is taught at the University of Waterloo in the fall term of 2021. All right, so in the last class we started to get into population representation. So we know how we wanted to get how individual neurons respond in relationship to something that they're representing. And we have a group of neurons, each of which are responding slightly differently to whatever it is that they're representing. We saw some examples of that. So for instance, here we have 3 different neurons, each and something, say for instance, how fast the rodent is running, and one neuron might respond this way. So as the rodent runs faster, we get a higher firing rate from the neuron. We have other neurons that sort of fire somewhere in the middle. We have other neurons that fire more for low speeds. The idea is if you have a bunch of neurons that are each responding in different ways, maybe we can decode interesting information from that. Okay. So one thing, the main aspect of the previous lecture was trying to systematize how do we set up this mapping between something being in the real world, so we're going to call this X, and the relationship between X and the firing rate of the neurons. And we called that the encoding equation. And what we ended up with was this thing down here, where there is some value in the real world being represented. Each neuron, and this X is a vector in general. Each neuron has some particular preferred vector, which we call its encoding vector, or preferred stimulus, or preferred direction vector. All these terms are synonymous. And this encoding vector, we constrain it to be a unit vector. We also have a scaling factor out. We have a scaling factor out here, and we have a bias factor. And then all that combination of things there, that tells you how much current is going to be flowing into the neuron. And then this G is the neuron model itself. So that might be our leaky integrate and fire neuron, or rectified linear neuron, or a big giant multi-compartmental model neuron, or so this G might be really simple, or it might be really, really complicated, depending on how much biological detail we're trying to pay attention to. But in any case, all of those things are going to just turn into some sort of activity. If it's for the more complex spiking neuron models that we'll get to in the next lecture, this activity will be a pattern of spikes over time. For what we're doing in this class, in this lecture right now, this activity might be just a firing rate, just a numerical value. That is, a larger value means I'm firing faster, and a smaller value means I'm firing not very quickly. But the argument was that equations of this form, we can take any sort of observed biological data and say, oh, okay, no, I could make neural activity look like the biological system by choosing my gain, my encoding vector, and my bias. Okay. All right, so that was encoding, and that was sort of the main focus of the previous lecture. Fine, we can encode information in a group of neurons. Encoding information in a group of neurons is kind of useless if you can't decode that information. And there's lots of different ways we might try to decode that information. What we're trying to do is find, this X got turned into a bunch of activities, and now we're just trying to find the inverse. We're just trying to find, okay, from those activities, can we figure out what X was? In general, we could try doing a bunch of really complicated math on this top thing to try to figure out what the actual inverse of this operation would be. But the worry with trying to do that is whatever complicated math process we're going to end up with, if it's a really complicated math process, maybe it would be so complicated that other neurons wouldn't be able to do it. It's one thing for us to be able to decode this information. If I have a bunch of activities trying to figure out what that X is, I can do all sorts of really complicated math and try to doing that. But if I'm trying to build up a model of like neurons connected to other neurons and passing information between them, I really should make sure that whatever math is going on to try to decode, figure out X given the activities, I should try to stick with math that I'm pretty sure that neurons could do. Okay. Again, this is this principle of add complexity, do things as simple as possible first, and then if you want to, add more complexity, but then since you've got the simpler version, you can then compare the more complicated version to the simpler version and see, do you gain anything by adding this complexity? This top equation here is as simple as we could find in order to still match what the biology, the tuning curves and the recordings that we see from brains. So this is as simple as we could get it. But what's the simplest possible decoding we could come up with? Well, the simplest possible decoding is let's just do something linear. Let's take our activities, multiply it by some matrix D. We're going to call our decoding matrix. And that's going to give us our estimate of X. Simplest thing we could do. How do we go ahead and find D? I quickly at the end of last lecture just simply said, just use least squares minimization, done. I want to spend a little bit more time on that just to actually step through that math just in case some people are interested, and it's also going to be a little bit irrelevant when we start getting into how do you deal with noise. The punchline is going to be, look, this is least squares minimization. It's a standard mathematical tool. Just use the built-in library that every sort of math tool has. But I do think for the purpose of this course, it'd be good to sort of let's spend a little bit more time on that. Right. So I'm going to switch over to, again, the course. This course has both the posted slides are posted on the GitHub page, but there is also a more complex, detailed set of notes on those GitHub pages. These notes were put together by Andreas Stockel, the PhD student who most recently taught this course, and he did just a really excellent job on that. So I'm just going to use his notes for those. I'm just going to cut down to where we start getting into this decoder. That's decoding values. Where he starts getting into this section. Right. Whoops, that's probably a little small. Okay. So, what are we trying to do here? What we're trying to do is we say, hey, I would really like to find the decoder where the difference between X and my decoded X, and we're going to use X hat, we're going to use this little hat symbol to mean the estimated value that comes out of, that we decode out, okay? And we're just going to be doing least squares minimization. We're going to say, okay, what's the difference, the norm of, because in general this is going to be a vector. If X is a vector, the decoded value is my activities, the activities for each X, multiplied by that decoding matrix. And we're trying to find the D value that minimizes this error. Okay? This error is also sometimes called a loss function. But this is what we're trying to do it. This integral, because we want, there's a whole bunch of different X values. This integral is sort of telling me, well, what range of X values am I going to be good at? Is it X values between -1 and 1? Is it X values between -10 million and +10 million? If this is a vector, then is it all the X values inside like a unit cube or a unit sphere or some space? You've got to choose some space that you're going to be optimizing over. And we want this integral. Fine. We're going to, because we're going to go try to work through this math, we're going to do a special case here. And we're just going to do the special case where X is a scalar, and we're only interested in X values between -1 and 1. Okay, it's not going to change anything about the proof. I could do any other areas as well. It's just going to really simplify the notation. So fine, how would we write that in that case? Well, fine, it's the integral between -1 and 1. We've got this square, the norm is the square root of x minus, the difference between x and that decoded thing. Okay, that's my vector of activities, all the different activities. This is my my decoding vector, and then we're doing the dot product between those two things. That's what's going to give us our estimate of x, our decoded value of x. And then we're saying, all right, x minus that squared, sum that all up, take the square root, everything's fine. We're going to get rid of that square root. We're just going to stick with that. Whether or not the square root exists, or whether or not there's that square root, the minimum is at the same point. So fine. This is actually what we want to take. We're just going to simplify everything down to just this. Fine. We're minimizing the mean squared error instead of the root mean squared error. They'll have the same mean, or they'll have the same minimum. In order to find the minimum of things, we'll even be a little bit more careful here. We're going to say, okay, hey, look, this is a quadratic equation. It's just a bunch of things being multiplied together, and it's just order 2. So we know that there's exactly one extreme point, and we know that it's going to be a minimum because this has a positive term. Okay, so we can do exactly the standard thing that everyone says whenever you want to try to take the minimum of something. You go ahead and you take its derivative and you set the derivative equal to 0. Of course, it means we got to take the derivative of this horrible thing, well, which actually turns out to not be too bad. Okay. Derivative of this, that all goes away, and what we're left with is these sorts of terms. Okay. Everything nicely rearranges. We've got these two terms. One of them seems to have the activities multiplied together times the decoders. One of them is the activities times x. Set that equal to 0. Okay. Do a little bit of rearranging. Horrible math, but it's not too bad. Yeah, well, it's ugly math maybe, but it is just this straightforward rearranging. One nice thing about this rearranging is this is a system of n equations and n unknowns, okay? Where n is our number of neurons, okay? And our unknowns are the decoders themselves. Okay. Great. That means we can treat this exactly like these sorts of matrix solving things that we do in sort of our intro to algebra classes. But we're going to need two separate terms. Okay. And fine, that's just going to build us two little matrices. Okay. And there's one matrix that is the activities of each neuron multiplied by the activity. So an activity of one neuron multiplied by the activity of the other neuron, and then integrate that over all the x values. And that tells you the entries in this matrix. And the other one is activities times the actual x value, integrated over all things. Okay. Fine, we can just go ahead. There is going to be this difficulty with this integral. The reason that's going to be difficult is, well, the activity is some horrible function. Like the activity, that's our neuron model, right? The activity comes out of our neuron model. So that's going to be some ugly, ugly math if we actually tried to take the integral over that. So what we do is we give up on doing this analytically, and we switch over to let's just sample things. Okay? And so we just instead of analytically doing this over all the x values, we just randomly sample a bunch of x values, or regularly sample x values. Just choose a bunch of different x values, go ahead and compute this, right? And then what the integral says is just add them all up. Okay? So that's exactly what we're going to do here. So this turns into this. Sampled, we're sampling somehow, and then of course normalizing, or scaling it, because that's our dx. Fine, we can do that twice. These things are going to cancel out. and then we're going to be left with these two terms. All right. So our decoder ends up being this. Oh, that's odd. There is going to be some slight inconsistency in notation. In some places, this thing here is written as capital X because that is the thing that is the big list of all X values. Whatever. Okay, so that I'm sometimes writing as capital X. So I'll see if I can fix that. All right. Maybe that math was useful for you, maybe it wasn't. The punchline is going to be, if I want to compute my decoders, this is my equation. See, here we go, now it's X. This X, that's what I was meaning, that's the same as this thing here. I'll fix that notation at some point. But what we have is, in order to find our best decoders, the decoders that do the best job of extracting information, or of trying to figure out what the X value was given the activities of the neurons, we have the A matrix that is our, for each X value, for each of the X values that I'm interested in, what is the activities of all the neurons? Okay. I take that matrix, I do that matrix times this other one transposed, take the inverse of that thing, and then multiply it by that. Okay. That's one way of doing that derivation, of doing that math derivation. In the lecture notes, I pointed out the other way of doing that math derivation. Again, we build up this A matrix of all the, we're sampling a whole bunch of different X values. For each X value, I can figure out what the activities are of each of my neurons. That's going to be make me a big matrix. And then I have my list of all of my X values I was interested in. We want this. I would really like it if my activities times my decoders gave me my X values. That would be great. I can't just divide both sides of this by A transpose. Matrices don't work like that. But what I can do is multiply both sides of this by A. I get A on both sides. Now over here I have AA transpose. That's a matrix that should have an inverse, assuming things are well behaved. We'll deal with that in a moment. But that AA transpose, that should have an inverse. So we go compute its inverse, and again multiply both sides by AA transpose. We get that. AA transpose inversed times AA transpose, that should cancel out. That's the whole point of an inverse. And so we're going to have this decoder, which is going to be AA transpose AX transpose. So that's two different ways of ending up with this same equation. Okay. Depending on what your math background is, you might like one way, you might like the other way, you might like neither way. In any case, the punchline is going to be, hey, build those matrices and then call this least squares function in Python, and it will give you the right answer. Okay. That's going to be where we're going to get these decoders. All right, so what's an example of that? We have this represented value X. Okay, so I'm showing this for this scalar case where X is a scalar between -1 and 1, although in general X can be any space. The reason I'm doing an example here with one dimension is I can actually make these plots in one dimension. I can't really make these plots in higher dimensions. But if it is this one-dimensional thing, and I've sampled across this x-axis, and for each of those different x values, there's some firing rate of each neuron. Okay, that's these plots. So each of those lines is a different neuron. This data that we're looking at here is the A matrix. Right? Across one axis of that matrix is all the different x values that I'm interested in. And across the other axis of the A matrix is the activity of all the neurons. So that is exactly the data given to this plotting function to say, go plot this. So that's our A matrix. We go and do the wacky math I just showed in order to find our decoder. If I multiply my activity matrix by my decoder, I should get my set of X values. Right? And that's when I do that math, I get this blue line. The dotted line is the ideal value. Right? Ideally, when I feed in an X of 0.5, I get these firing rate patterns. Right? I then do my decoder, and I should get out the value 0.5. Right? And I get out a value that's pretty close to 0.5. Okay. It's not perfect. It's not exactly on the right line. If I actually take that difference and plot the difference, you'll see, oh, okay, like we're within 0.2, 0.3, 0.4, at different points across the x-axis. So this is sort of an indication that this simple assumption that I made of, look, let's just do a linear decoder, it's not bad. Right? A linear decoder does a pretty good job of pulling out exactly what that x value was. Cool. Except there's one extra twist we got to add on here. There's noise in biological systems. Well, actually, any physical system. There's a whole bunch of sources of noise in biological systems. Those spikes that are coming through the system, they, sometimes are moving slightly faster, sometimes slightly slower, sometimes, fading a little bit more, sometimes not. When those spikes hit the end of a synapse and they release neurotransmitter to go and communicate to the next neuron, sometimes it doesn't release neurotransmitter. This is called vesicle release failure. So sometimes the spike is just totally ignored. When a spike hits this end of this neuron and neurotransmitter is released, well, the way that works is the spike hits this top thing. This is the neuron that is spiking. This bottom thing is the next neuron. That voltage spike comes along here and starts attracting these little vesicles that are filled with neurotransmitter to the edge to the cell where it's going to burst open. So sometimes just nothing gets attracted and nothing bursts open. So that's the vesicle release failure. But it's also, well, how much neurotransmitter is in each of these things? All right, sometimes it'll be smaller, sometimes it'll be bigger. That neurotransmitter, what it's going to do is it's just going to open and close channels, ion channels, to let current in and out. But that's a stochastic process. Right? Are these neurotransmitters actually going to bind to these proteins? Is stuff going to actually happen? Noise. All of that stuff is happening. There's thermal noise because this thing is not at absolute zero. Tons of noise in these systems. Okay, and even if none of that sort of stuff existed, the fact that there's spikes coming into this system is just going to mean that everything we're doing so far has just been about averages, and at any given instant we're not going to be at the average. So, all right, tons and tons of forces of noise. We're going to have to model that somehow. Again, what's the simplest possible way of modeling that? Well, if someone says, do you want to add randomness to a system? The default for all mathematicians is just let's add Gaussian noise. Okay, so we're going to add, in this case, where we don't want to model all this stuff, we're going to add Gaussian noise. When we start doing a more complex neuron model, then we can relax that assumption. Okay, but Gaussian noise is fine. Let's make sure that we're taking noise into account. So what happens if we take our population tuning curves and add a chunk of noise? So we actually get things like this, and then we try decoding it. Oops, and those graphs are not as bad as they should be. I'm going to go cut over to this where we're actually going to see them. Oh, I guess it's not too bad. Okay. Right. Sorry, where are we? There we are. What we're kind of showing here is you add noise. Right, so that line was like nice and clean, right? Okay, I add noise to the system, and now my decoder is just way worse. Way worse. Okay, this is just problems. Okay, so what's happened is when we solve for the decoders, we were solving for the decoders, not taking noise in, or assuming that the activities were perfect. What we really want to do is we want to find decoders that are robust to noise. How do we go ahead and do that? This is why we went through that little bit of wacky math, because yeah, it's going to make it a little bit clearer why we're going to do, or what it is that we're going to do to deal with this noise. Because when we went ahead and computed those decoders, so we weren't taking noise into account, and there was a couple other issues that some people might have twigged into when we were going through that math. At one point, we did the inverse of AA transpose. Nothing guaranteed that that inverse is possible. Okay, if you've got neurons that have very, very, very similar, or if you have neurons that have identical responses, or a neuron that doesn't fire at all, then what you're going to have is you're going to have situations where rows and columns in A are linearly dependent. You won't be able to get a perfect inverse. Okay. More practically, even if AA transpose is invertible, there can be some problems in inverting it because we're going to, we're running that inversion on a digital computer. Digital computers, if you have matrices that are almost uninvertible, or almost have row columns that are almost linearly dependent, then you can get numerical stability issues. Okay? And that's going to, basically, in practice, that's going to happen if neurons have very, very similar parameters. Then you're going to have rows in that A matrix that are almost identical to each other. That's going to lead to numerical instability. So, we want, now the fun thing is that it turns out by taking noise into account, these two problems also go away, which is kind of nice. How are we going to take noise into account? Well, what we really want to do is we're still going to be minimizing this, we want to minimize this error, but we want to do it assuming the activity has some amount of noise being added to it. Okay? And for this math, we're going to assume Gaussian noise, basically because if you assume some other distribution of noise, then this math becomes ridiculously complicated. The whole reason that all mathematicians really like Gaussian noise is Gaussian noise has lots of really nice math properties. So there's going to be some Gaussian noise with some variance, and that's going to be added to our activities, and everything else about our minimization problem is the same. So we go ahead and fine, we do this math, we go and bring this, this squaring is going to be a problem, but this noise term has some really nice properties. In particular, because you know this noise has mean zero, a whole bunch of these cross terms cancel out. It's certainly also the case that when the sum that's going to be of all of these terms together, down here, we've got decoders multiplied by each other, multiplied by the expected value of two Gaussian noise terms multiplied together. Well, each of these, that's the noise on each individual neuron. So all of the sums here where I is not equal to j, yeah, those are all going to disappear because those expected values all become zero. Cancel, 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 cancel. The whole thing goes away. And basically what we're left with is we're minimizing this thing, which is the same thing we were minimizing before, plus this new term. And this new term, so that's where these sums, the I and the j, were the same value, because that's going to be the situation where things are not going to cancel out. We're not going to have an expected value of 0. We're going to have the expected value of the square of a Gaussian variable being multiplied by my decoder. Well, the expected value of the square of a Gaussian is, that is the definition of variance. So, all right, that's the variance, and we're left with this. So this is sort of our add-on term. We're trying to minimize something. This is our, this is our minimize the decoding error. Exactly the same, when we're not taking noise into account. Same equation as before. And we've added on this new term, which is related to the variance of the noise, and multiplied by the square of the decoder value. What the heck is that? Conceptually, what we can think of what this is doing is and we're trying to minimize this whole value here. So this thing is trying to minimize the error, the decoding error. This thing is trying to minimize the magnitude of the decoders, right? Because this term over here is going to be small when the magnitude of the decoder is small. People may have seen this before. This is regularization. This is a really common math thing that is going to turn up. Basically what this is doing is this is a penalty term on having the decoders be large, because, and sort of intuitively, if a decoder is large, that means it's just going to amplify the noise, right? The larger the decoder value gets, because the decoder is going to be multiplied by the activity. If the activity is huge, if the activity has some noise on it, right, then that activity times some decoder. The larger the decoder is, the larger the noise, in fact, the noise is going to have. So intuitively, that kind of makes sense. Comes nicely out of the math. And then if you go ahead and do that, you're going to get improved accuracy. Okay. Just because it is relevant, it is worth, it's a very surprising result, a very widely known result, but it's still a surprising result, that doing least square, doing this sort of least squares solving, assuming there's Gaussian noise in the system, the fact that that's exactly the same as what's sometimes called L2 regularization, or minimizing the norm of the thing that you're solving. So yeah, that's a widely known result. Sometimes people call this a regularization factor. It's there. So, all right, what did I want you to get out of that? All of that math just simply says, all right, there is a technique, a very standard, widely known technique about how to deal with noise in the system, and it just turns into a penalty term. If we go through and do the math, the way that you do it is when you do this AA transpose, the thing that you're about to invert, what you end up needing to do is you end up needing to take the variance, how much noise you expect there to be, multiply that by the identity matrix, and multiply by the number of samples, just to keep everything in the same scales, and then you're adding that onto this AA transpose. Okay. Because this is an identity matrix, you're going to be adding values onto the diagonal of the AA transpose matrix. That's why this is sometimes called ridge regression. You're adding values onto the diagonal of a matrix before you invert it. The other cool thing that does is it makes sure that AA transpose is always invertible, and it's going to be nicely numerically stable. Okay, cool. Maybe all that math made sense to you, depending on what courses you've had. Maybe you're just like, okay, sure, I'll accept the final result. How do I do that? How do you do that is, all right, you add in that term when you compute your AA transpose, and you go ahead and add in that term. Okay. Cool. And that will go ahead and reduce, significantly reduce your error of your system. All right. So, what does all of that mean? We're building models. Okay, so do a quick summary of that, and then we'll do a couple examples. When we encode information in a group of neurons, our assumption is we are going to be using, the simplest thing we can come up with that gives you neurons that seem to respond in the same sort of way as we see in biology is this equation down here, where for every neuron there is some, so there's some space x being represented. In this particular case over here, it's a scalar between -1 and 1. Every neuron has some preferred stimulus, which is a unit vector in that space. The only two unit vectors in a one-dimensional space are -1 and +1. So for all of these neurons, the only options are -1 and +1 for EI. Yeah. And you can pop out and you can see, oh, hey, look, all of these neurons here that have larger values for larger x, those have encoders of +1. For the other ones, the ones that are larger down here, those have encoders of -1. But then each of the neurons have different sort of scaling properties and are sort of shifted back and forth different amounts. That's going to be controlled by this gain parameter that's different for each neuron and this bias parameter. The gain parameter is strictly positive. Bias parameter can be whatever it wants. One way to think of the bias parameter is if x is 0, well, this whole term over here is going to be 0, but you still want the neurons to be doing something, and each neuron is doing something else, something different when x is 0. Right? When x is 0, this neuron is here, this neuron's firing there, this neuron's firing there, this neuron's firing a lot. Okay? Whatever current causes that amount of firing, that's what the bias value is. Okay. In general, where do we get these gains and biases? Because these are things that you're going to be computing in the first assignment. One simple thing that we tend to do is we tend to say, well, look, we probably want all of these neurons to have some intercepts somewhere in this space. Right? It's kind of useless to have a neuron that hits this x-axis, say, way out here. I could find a gain and a bias value that would cause a neuron to start firing here, and then across this part of the space, it would just sort of have some little curve like that. The reason that's kind of useless is, well, that's basically a straight line, and the whole point of a neural network is to introduce nonlinearities to let you compute things, so a straight line's kind of useless. So our general assumption is you want to have intercept somewhere within the space that you're using. Oh, you definitely don't want a neuron that starts firing out here and goes that way, because that'd be a neuron that doesn't fire at all in this range. So, so our sort of default assumption that we'll be taking care of in this course is let's have the x-intercept, the place the neuron starts firing, somewhere in this range. And we might say have a maximum firing rate in some other range. Right. So say between 100 hertz and 200 hertz. Given those two constraints, you can go and back derive, okay, what would be the gain and the bias for any particular neuron. That's something you'll be doing in the assignment. The reason that we tend to do it that way is those tend to be values that you can take a look at the neuroscience literature and figure out what they're going to be. And you tend to find neurons with this sort of uniform distribution across there, or some other distribution. Tend to be able to squint at the neuroscience data and see that. But the other thing you will often definitely get from the neuroscience data is, well, what sort of range of maximum firing rates do you see? It's very, but that's not, you won't find in the neuroscience data, exactly what gain and bias should be, because that's an incredibly difficult thing to go ahead and measure. But these things you might be able to measure. Cool, but that's how we're going to do encoding. Decoding, simplest possible thing we can come up with is linear decoding, which is take your activities, multiply by some matrix, and that gives you your x. The way that we're going to find that matrix is we're going to use this equation here. All right, where we're going to pick a bunch of different x values. We're going to get our activities for each of those x values. We're going to go compute this wacky thing here. So A being the matrix with all the different activities. We do AA transpose, that's a big square matrix. We add a regularization term along its diagonal in order to take noise into account and also make sure it is invertible. We invert it, multiply by the activity matrix again, and multiply it by x, the thing that we know the answer is supposed to be. That gives us our decoder. That gives us a nice line of, cool, all right, we're going to represent these values. So how well does that work? That's going to depend on a lot of things. It's going to depend on exactly what the neuron model is. It's going to depend on how many neurons we have. The graphs I'm going to show right now are, it's also going to depend on exactly what these distributions are and what our firing rate distributions are and how much noise there is. The graphs I'm going to show here are going to be for leaky integrated fire neurons, and with that same distribution I was just showing of their tuning curves. And then what we're going to say is, well, that error, when we went and did that math about where the heck that error was coming from, well, it's actually going to come from two different places. Okay. So one aspect is, well, how much error just was there in this inversion, just ignoring noise? So if there was no noise at all, finding X, we take X, we go and code it in a bunch of activities, and then you try to decode out back what X is. We don't get out exactly X, even if there was no noise whatsoever. Okay. So there is some distortion just due to the just due to the fact that we are taking an X value, we are encoding it in a bunch of neurons, and then we are trying to extract that back out linearly. Okay. That's this plot over here. And what I'm plotting here is what happens to this distortion as you increase the number of neurons. Okay. And then what we're doing, as I increase the number of neurons, we can see this sort of coming down at some reasonably regular rate. What we're showing here is that the squared error is coming down about as n squared. Right, that's sort of this graph here. It's not perfect, but that's about what we're trying to see here. That this is the error due to the static distortion, okay, or sort of the non-noise aspect. So just, hey, look, our encoding is not perfect. But then there's also the sort of noise that I was saying here is of, hey, look, any noise in the system is going to get amplified by these decoders. Let's go ahead and compute what that is going to be like. And that is going to, again, as I increase the number of neurons, we are going to get this, this dropping down about as 1 over n. Again, that's a plot that you will have to make in your assignment. So you're like, okay, cool. As I increase these, and literally we can just compute this. Once you've solved for that system, once you've solved for those decoders, you can compute the error for the distortion. That's easy. That is just literally, well, take your activity matrix and multiply it by your decoders and your x hat, and what's the difference between x and our actual decoded value? Squared, of course. This is squared error. If you want squared error. So that's computable. And then this one over here, well, that's also nice and easy to compute, because that's just literally, we'll take your decoders and do this math on them. And so we can go ahead and make that. Cool. So we can at least get some sort of sense about how many neurons are needed to get a certain amount of accuracy. All right. And we do have this nice sort of property that as we increase our number of neurons, our representation gets better, and we can see by how much. And that's going to be kind of cool if we can sort of look at biological systems and say, like, oh, well, this biological system uses 30 neurons to do this task, and this biological system uses 1,000 neurons to do this task. Which one's more accurate? Right? And by how much? Is this, we can go and test that. We can go look and say, holy look, is the increase in accuracy about what we expect using this sort of method? And okay, so we'd actually start at this point. We can now sort of start looking at actual biological systems and seeing, does all of this math that I just talked about sort of vaguely make sense for these systems? Cool. So let's start that. The one that when this methodology was sort of first invented, one of the very first examples that we're sort of applying to was the horizontal position of an eye, because this is exactly the situation where, there are, this is a system that appears in lots of different biological systems. in, I think it's goldfish, there's like 30 or 40 neurons doing this. In humans, it's something like 1,000 neurons. You can take a look at the accuracy difference. Right, this is extremely well analyzed. You can go ahead and take a look at, okay, let's go measure from these neurons. And depending on what the eye position is, here's 2 different neurons. All right, depending on their eye position, all the way to the left or all the way to the right, I get different firing rates. Yeah, that's one neuron. And here's another neuron. And it turns out these things have ridiculously straight lines. So these, the particular neurons that are involved here have, very, rephrase this. If we go back, in lecture 2, when we're actually looking at leaking rate and fire neurons, there's 2 parameters. One is the refractory period, how long it takes for the neuron to recover after firing, and the other one is the membrane time constant, how long it takes for charge to, or voltage to build up and to collapse back down as it's recovering, or to leak back out. And it does actually turn out that the that the actual, in the biological system, you tend to have neurons that have a fairly low refractory period and a fairly high membrane time constant. So you do get these nice straight line neurons. In general, in those neurons, you actually do get encoders that are both +1 and -1. So you'll have some neurons that look like this, and you'll have some neurons that look the other way. And you do not, in this system, get neurons that are sensitive to like something in the middle. Okay. Just they aren't observed. And we get fairly high firing rates, up to like 300 hertz. So those are all things you can go look at the neuroscience data and and say, oh, okay, that's cool. All right. And just from looking at the task, you can sort of say, okay, well, what's being represented? Well, the position of the eye. Is the eye to the left, is it to the right? What's the horizontal position of the eye? So when we're going to go ahead and build a model of these things, this is exactly the sort of the 2 first steps that we end up doing. We end up saying, all right, what's being represented? Position of the eye. What do we know about the biological details? In particular, what do we know about the tuning curve shape? And those are sort of the first steps. This is sort of trying to think about at the high level what's being represented, and this is sort of at the low level, what's the details of our tuning curves. We then go ahead and say, all right, we need to nail down this definition a little bit more. In particular, whenever we have a variable being represented, always get into the habit of saying, well, hey, look, what's the range of values on this? Because in all of the graphs I've shown so far in this course, there is some sort of range that things being optimized over. Okay. And when we do this optimization to find D, we need to pick some range to be sampling over. Okay. So it's always going to be the case that, we're never going to be representing values between -infinity and +infinity. It's just not going to happen. So you always want to get into the habit of, whenever I've got a variable being represented, well, what's the range? Again, horizontal eye position, I got limits on that. There's going to be some sort of range of values, that it's not going to go past. Cool. Amount of noise is sometimes a little bit trickier to figure out what a good value is. Sometimes you can dig that out of neuroscience papers. Sometimes we just sort of, let's just stick with a default of, I don't know, systems are pretty noisy. Let's, 20% of the maximum of whatever the activities are. We might pick something like that. It'd be great if we have more detailed values to nail that down a little bit more. Mostly what we try to do anyway is at least get things, if I don't know, I'll pick a large value like that, and hopefully nail it down later. But once we do that, we can then go ahead and build our model, and generally what it's going to go consist of is, all right, that means I got to choose all my tuning curve parameters. That is, choose my encoders, gains, and biases to make things match how I want. and then go ahead and solve for my decoders. And that'll give me a sort of a basic model of the horizontal eye position. Okay. That was one of the first things that this was applied to. Later on in the course, we'll see a slightly more fancy example of this, where that it turns out that the horizontal eye position needs to do a calculation because the input to that system turns out to be the velocity, which turns out to be, oh, I need to change x by some amount, which means the system not only has to represent x, it also needs to compute the integral of its input. So when we go ahead and actually compare it to the biological data, we'll wait until we get that sort of fancier calculation. But as a basic setup, that works fine. That would be an initial model for making horizontal eye position stuff, representing a value. What's a more complicated example of representing something? Another very standard, so early on result that really established this idea of neurons having preferred stimuli was some work from Georgopoulos about arm movements. So this is a bunch of experiments where you would have a monkey staring at a screen, and dots would appear on the screen at different locations, and the monkey had to move a joystick towards the location of the dot. And in some variations, the monkey has to remember the location and then move the joystick. In some variations, they just have to move the joystick. But in any case, what you're doing is you're recording from different parts of the brain and trying to see, okay, how is that representing the information about where I want to move to or what direction to move in. And what they ended up finding pretty clearly is, hey, you can find neurons that, depending on which direction the monkey is supposed to move its arm, you can find neurons that respond to different directions in this space. This is one particular neuron. So what we're seeing here is all this recordings on the screen is from the same neuron. The different rows are different trials. Move to the upper left. Move to the upper left. All right, I get this firing activity. Move to the upper left again. I get this firing activity. This one. If you look closely there, what you're seeing there is what I was saying about noise. Even if it's doing exactly the same task on different runs, you're going to have different amounts of noise. This would be a situation where you could sit down and go ahead and analyze those spike data streams and try to figure out what a good estimate of the amount of noise is. But in any case, that's what's going to happen when the monkey's moving to the same direction. But then what we also have is, oh, well, what if the monkey's moving in a slightly different direction, or a slightly different direction, or a slightly different direction, or a different direction? Okay. And what you end up finding is you've got some direction that this neuron really likes, right? This neuron in the monkey, and as you get away from that direction, the neuron activity drops off. And if you're going totally opposite direction, then the neuron activity is even lower. And you can see that plot right here. Right? So this would be sort of a classic, there is a preferred direction for this neuron, and things drop off on either side of it. Okay? And of course, there would be lots of neurons, and each neuron would have a different direction in the space. And the way we would think of that, of course, is that different neurons would have different preferred stimuli. Sorry, let me go all the way back to this graph again. In this particular case, X would be two-dimensional. Each neuron would have an encoder that is a different direction in the two-dimensional space. Okay. Again, they're all unit vectors, so there'd be different directions around the circle. Then they'd have these gains, and they'd have these biases. That would give us our activities, and then we would solve for our decoders. Interestingly, in the work where Georgopoulos sort of established this, 1982, basically did exactly what we're talking about for building up those activities and saying, okay, look, there's going to be some preferred stimulus from preferred direction for each of these neurons. That was all, that just was incredibly clear from that. But the way that Georgopoulos decoded was not what we were doing. Right? Like it's almost exactly the same setup. Right? We've got this very clear sort of, okay, cool, here's a bunch of neurons. They've got different firing rates. the firing rates are going to be maximal for some particular direction. But Georgopoulos did not do the step that we did of saying, okay, let's solve for the best decoder. Instead, what Georgopoulos ended up doing was saying, well, I know I can look at each of those neurons and I can figure out, well, what that, just from the activity of the neurons, I can figure out what E was. Right? I can go ahead and figure out the E value for each neuron, because that's just the direction that causes that neuron to fire the most. And then what Georgopoulos ended up doing is saying, well, okay, instead of finding a good decoder, let's just use E as my decoder. Right? That was the idea. So it was just sort of, all right, let's estimate that X by taking the activities and multiplying them by E, by my encoder, what the direction is. That gives a pretty good, so by definition, it's going to be worse than what we've just done, because what we've gone and solved for is the optimal decoder. So any other decoder must be worse, just by definition. But this method is actually a pretty good direction estimate. It gives a decent sort of, okay, what is the overall direction of the movement? Horrible actually knowing how far, from that information, trying to figure out how far the monkey's planning to move, not a chance. So again, if we want to think of this as like the X that's being represented is the XY value, right? This method turns out to be decent at figuring out theta, the angle, but it's really good it's really bad at figuring out the radius, the magnitude of the vector. But this approach definitely exists. It's been out there. Again, in your assignment, you will go and compare the actual our method of doing decoders to this approach. Yeah, by definition, this is going to be worse. But it can also be really, really simple because you don't have to go solve for decoders. Again, you want to go ahead and build this model. We have to, choose X, the movement direction, what is being represented, the hand position, the place you're trying to move to, the position on the screen that you're trying to move to. You're going to choose an X value. You've got to choose how you want to do that X. And again, this would be an example. Do you want X, if I've got some position on a screen to represent, I might choose some different approaches. I could specify that as an XY location, like X versus Y, right? That would be a two-dimensional vector. I could represent that as radius and theta. That's another way of representing a two-dimensional thing. It's going to turn out that if you want to make, the thing that helps you make that decision is, well, look, what are the tuning curves that I want to make? And the tuning curves, I can get the sorts of tuning curves that we observe in the biological system if I choose X to be the X and Y position of where I want to represent, and if I choose my encoders as randomly distributed along the unit circle. Okay. And then I also got firing rates up to some amount that I can go measure. My range of values that I'm going to represent, that's a little bit trickier. You got to figure out, okay, well, what possible XY values? Again, it's not between minus infinity and plus infinity and on the x-axis and minus infinity and plus infinity on the y-axis. I've got to choose something. The default that we tend to make in this course, because rectangles don't really exist in physics, well, maybe they do, so you could choose a rectangular sort of, okay, there's some range this way and some range this way, and you're optimizing across that rectangle. It feels a little bit more natural to choose a circle of a limited radius and optimize across there. We tend to default to the circle approach rather than a rectangle. You can maybe make an argument that the circle approach is just making a few simpler assumptions. It does mean that you don't get anything weird special happening at the corners, which is nice. So we'll tend to choose circles, and sort of saying, okay, all the x values inside some circle. And again, we got to choose an amount of noise. We might be able to get that out of the neural activity data. But again, in this one, we'll just put in, say, 20% of the noise. Choose our tuning curve parameters, compute decoders, and we can build our model. All right. I think last example that we have here is I guess in the vestibular system. There are neurons that are sensitive to acceleration in 3 dimensions. Here's kind of a weird situation where, again, you can go record from these neurons, see what they're doing. It turns out there, even though this is a 3-dimensional space, and you're like, oh, well, maybe, are we randomly choosing vectors in a 3-dimensional space now, and each neuron is sensitive to a different combination of accelerations? That's one way it could have been. It turns out, if you go and look at the biology, no, each neuron has some particular axis that it's sensitive to and not sensitive to the other ones. Okay, that's partly because the actual physics of the system that's detecting these rotations is split into 3 different loops, and the neurons that are sensitive to one of these loops are looking for accelerations along this axis, and then this axis, and then this axis. And so, all right, that fits our models perfectly fine. It's just instead of randomly choosing encoders from a 3-dimensional space, right, we're going to choose, there's only 6 possible axis-aligned encoder vectors. So we've got 1 and -1 on one axis, 1 and -1 on another axis, and 1 and -1 on the third axis. So you can build models that way as well. All depends on the biological system. Why might you do it that way? As far as we can say right now, from what at this point in the course, one small thing we can see is, yes, if you do have separated out axes, you do have a slight improvement in how well you can represent things. So your error is slightly lower if you separate out your axes like this. Okay, so that's cool. There's going to be a drawback, though. And we will get that later in the course when we start getting into, well, I want to do more than just represent data. I want to also do computations on that data. When we do this separating out, that's going to turn out to have some limitations on what computations I can make. Okay, cool. That's going to be a really nice example where we can start saying, all right, depending on what you want to do, what the neural system wants to do with this data, we might be able to say, okay, you can get away, may as well take advantage of this extra accuracy if there's simple calculations that you're going to want to do. But there's going to be situations where you don't want to do that trade-off. But that's stuff we will cover later in the course. Okay, that is lots and lots and lots of stuff. What all are we going on about this? You now have enough information to do assignment 1. Due date's October 4th. Please work at it. Again, I will iterate. Please, discuss the assignment with people in the course and ask questions in the Slack channel. Everyone is required to submit their own code, their own answers, their own graphs, and no, that does not mean that you can just word-for-word copy from someone else. But in any case, go ahead. You're basically going to be implementing everything in this lecture that I just gave. That's going to be assignment 1. Please go ahead and do that. And what we're going to do in the next lecture is go on to what happens when we take spiking into account. Because what we've done so far has all been just sort of assuming that we can get away with ignoring spikes. But we want to sort of say, okay, well, if we add in this extra detail of spikes, what can we do? How much is that going to change what we've just shown? All right. Cool. We will see you in next class. Thank you very much. Bye.